Any other questions? No? Okay, so let's discuss another type of method called Gauss Seidel. If you remember, the equivalence of Jacobi is we decompose a matrix when we solve for AU equal to B. We decompose A into D plus L plus U times U equal to B. And we take this into the left-hand side and L and U to the right-hand side. We have du of k plus 1 is equal to B minus L times U minus U times U, both at k. Gauss Seidel iteration is a small modification to this. It says, okay, I'm going to have both D and L on the left hand side, and only move U to the right hand side. Now, instead of solving for a diagonal matrix, we need to solve for a lower diagonal matrix, a matrix that contains a diagonal and a lot of stuff underneath the diagonal. Does it make solving D plus L hard? Surprisingly, there is a technique to solve a lower diagonal matrix that is almost as easy as solving a diagonal matrix. That's called substitution. Actually, in this case, a lower diagonal matrix, you start from so if you have a lower diagonal matrix like this, times UK plus 1 is equal to something. The first entry can be solved immediately because there is only one entry on the first row. And then once the first row is solved, when you go to the second row, there are only 2 entries. And the first entry is multiplied by something you just have solved. So you can solve this entry, the second entry, as easily. And as you go forward, everything you have already solved can be used in all but one non-zero entries on that row. It's called forward substitution. And somebody also mentioned backward substitution. That is used for solving an upper diagonal matrix. Yes. Okay, so this is Gauss Seidel, and in practice, Gauss Seidel is very easy to implement. So let's actually go to our multigrid. So for example, when we want to do Gauss Seidel, we can comment this out. And by the way, Gauss Seidel has an eigenstructure that is different from Jacobi. It doesn't go all the way to -1, so you don't actually need on the relaxation for it to be a good smoother. Okay, so let's call Gauss Seidel. Okay, and let's actually also do the same thing for the post smoothing and comment out the under-relaxed Jacobi. I try to save it. And let's copy the Jacobi. Where is my Jacobi? Copy and paste. Paste. Okay. Let's call it Gauss Seidel. Call it Gauss Seidel. And in MATLAB, you need to make this function name the same as the file name for this to work properly. And so the only thing different is instead of just solving the diagonal matrix, we do forward substitution. In forward substitution, we use the solution we have already solved. We use the part of the solution we have already solved in this iteration. So U next has already been solved for any I and j that is less than the current value, right? Okay, so remember our outer iteration is on I. So U next of, first of all, I minus 1j is already solved. So we can use U next I minus 1j in this iteration. That is, this term is the lower diagonal part of the matrix. Okay, let's go back. Is this term lower diagonal or upper diagonal? Upper diagonal, because I plus 1 hasn't been solved yet. So should I use U or U next? Should use U, it should be on the right hand side. It's part of big U times U to the kth. And how about this? It's also upper diagonal. It should be UK. How about this? It's lower diagonal. Should be L times UK plus 1. It should be U next. U next in this iteration is UK plus 1. So okay, we have changed Jacobi iteration into Gauss Seidel. It's that simple. And let's try this again. Initial condition equal to 0. Multigrid. No. UB. And I'm only doing 3 and 2 iterations. So let's see how the residual has been reduced. See, the residual has been reduced. It's actually better than the Jacobi case, right? So it gone from 10 to the 7th to 7 times 10 to the 5. Remember, when we just do on the relaxed Jacobi, it's still like something times 10 to the 6. All right, any questions on the Gauss Seidel iterations? So why we don't always use Gauss Seidel iterations if it works better than Jacobi and don't need on the relaxation? Yes. It depends on the sparsity of the matrix. Yeah. Yeah, but like you can always use it, right? Like that. Yeah? Any ideas? Yeah. Yeah, you have a very good point. So the Gauss Seidel is a you call it non-isotropic way, right? It's an inherently sequential algorithm. You need all the previous grid points to be solved before you can solve the next grid point, I in J, right? That's what you mean by non-isotropic, right? You are solving some part of the solution first, and you need that part of the solution to go to other parts of the solution. It's sequential. And if you are having a parallel machine or just a solution, a processor that supports like vector operations, this is not very efficient. While Jacobi, it's a very parallelizable algorithm, and both in the distributed memory level and on the vector operation level. So Jacobi iteration is slightly better in its performance if you only count the floating point operations. But for other considerations, it may not be the best algorithm. All right. Any questions on Gauss Seidel? No. So there are other more powerful iterative methods you can use as smoothers in multigrid, but we are not going to be talking about that. So MATLAB has a lot of these iterative methods like conjugate gradient, GMRes, MinRes, and a lot of these. And I believe there is another class at MIT that really dives into these iterative methods, right? Who remembers what course 9 was? Huh? Yes, right. Introduction to Numerical Methods. Okay, so yeah, so there is another class that like really talks about different type of iterative methods. We don't have time to do that in this class, but if you're interested, you can learn more, and most of these can be used as smoothers in multigrid, at least in combination with some kind of under relaxation. All right. Okay. One thing I want to point out is why do we need pre-smoothing at all? And one of the pitfalls in multigrid, if it can't make multigrid work, that's one of the top reasons why. That is, your smoother is not able to reduce the high frequency content of the solution error sufficiently. And if you're not able to reduce the high frequency content sufficiently,